Hello everybody, I just want to let you know, that you know who is sitting here doing calculus with us. Alright, so we want to expand what we can do now that we're really super good at doing integration, aka antiderivatives. So now, what are they useful for? Well, the first thing I know is that when I'm doing this indefinite integration, remember the other name for it is antidifferential. So here I've given you a few examples of a differential equation. Notice they all have either a first derivative or second derivative involved. And so, of course, I know on some of these how to actually get the general solution now. Remember, I'd be powering up, so that would turn into an x squared and divide by the new power. The coefficient stays in front, and coefficient stays in front, and now remember this before was x to the 0, even though we didn't write it, so now it's going to be x to the first, and divide that by 1. Same thing here. I can power back up, so I'll get x to the third, and of course I'll have to divide by 3, so I could write that as a third. And again, this is x to the 0, so when I power back up, it'll be x to the first divided by 1 with a coefficient of 1 inside, or in front of it. And on this one, we haven't, on this next one, I have a second derivative, but we haven't actually practiced yet on what we're going to do to get back to first derivative. I could get it back to first derivative, and then same thing down here, I got a second derivative. Oh, and did you notice that on these I forgot to take my vitamin C? There is a C here, which is what makes it a general solution. Okay? So when a problem says solve the differential equation, what it's asking you to do is get back to the original equation. In other words, even if you're at second derivative, get all the way back to f of x. But here's the problem, is that initially all we're going to be able to find is a general solution. And if we want a particular solution, we're going to need a little more detail. And that detail is that we need some initial conditions. And if we use those initial conditions, we'll be able to solve and find our constant, aka C. So here's my first differential equation. Remember, this is really f prime of x equals 2x. And notice that I have some extra information, and that the original problem, so f of x goes through this point, which means, of course, I know x, and I know f of x at a particular spot on that curve. So the first thing I'm going to do is I'm going to differentiate, I'm going to integrate my function that's in derivative form. And of course, when I do that, I'm going to power back up, so that'll turn into a 2, which means I divide by 2. And then of course, these 2's are going to cancel, so I get x squared plus c. And of course, that is my general solution. But now I know that, and oh, by the way, this is in fact f of x. But I know that I have this initial condition up here that in my function, when x is 2, y is 5, or f of x is 5. So that means I can simply plug it in, So now it's going to look like this. 5 equals 2 squared plus c, and when I solve that out, of course, I get c equals 1. So now I can write the specific or particular specific solution or particular solution, which is f of x equals, so I'm pulling right off of this, so it's going to be x squared plus, but now I know c. And so there is my solution. So again, working on this, the first thing I need to do is take the antiderivative of that first derivative. And of course, remember we talked today about good communication, so I can split them. That coefficient could go in front. Notice how each one has the integral symbol and each one has the dx, so I know what I'm integrating with respect to. And of course, I'm powering back up, so that first one is going to turn into x. Remember, it'll be to the first and divided by 1, but I don't need to write that. And then minus 6 powering up and dividing by the power. And I'll reduce that in a second, and don't forget my vitamin C. And of course, this is the original function general form. And so now, if I use my initial conditions, so this is general, again, I can simplify that in the center to -3. But what I know about this function is that when x is 0, y is 8. So that means I can plug in and I'll have 8 equals 0 minus 3, 0 squared plus c, which tells me c is 8. And so that means I can write the specific solution, which is f of x equals, I'm going to put this in front since it is the leading term, so negative 3x squared plus x plus 8. So let's try another one. So I have to take the antiderivative of that derivative. Remember, good communication, what variable we're integrating with respect to. And of course, I can split them. Coefficients to the front, please. Oops, I forgot to put the dx in here. We'll squeeze it. Okay, so now when I integrate, I'm going to get, actually we're going to do this. We're going to write f of x equals, so the antiderivative cosine is sine, and the antiderivative of sine is negative cosine, so that'll turn this into a negative term, plus c. And of course this is the general solution, but we'd like to find a specific solution, and since we have some information about the original function, we can plug in, so 4 for the y, and 0 everywhere I have an x. And I hope you're thinking in your head really fast what sine and cosine of 0 are. Of course, sine of 0 is 0. Cosine of 0 is 1, so that's going to be a negative 5, plus c. So then c is 9. So now I can write the specific, easy for me to say, specific solution, which is f of x equals 3 sine x minus 5 cosine x plus 9.